Okay, I want to continue our discussion about probabilities and about inferential statistics. And we're going to, in this video, talk about what I think is the most complex and maybe challenging concepts in the whole course, and that is something called the Central Limit Theorem. But we'll get to that in a minute. One of the things that we left off in the last video talking about trying to guess the parameters of a population, and specifically we were trying to make a guess about the mean, and we'll eventually make some guesses about standard deviation as well. But I shared with you, that I have this bag that has a distribution of 25 scores in it. And we're trying to make a guess about what is the mean for this population. And again, we'll get to the standard deviation. You might anticipate that it would be better if we could take more than one block out, right? Instead of just taking one block, could we take more than one block? We might get a better idea of what's going on with the population. We left off in the last video. I had pulled out a block with the number 14 on it, and we said, well, that is my guess for the mean of the population of the 25 blocks in the bag, not because that's the only thing we had. And we have to get rid of that logic because it's not very compelling. But we're going to sort of think about it in a different way, right? We're going to say, well, what do we expect to pick from that bag by chance? That is, what has the highest probability? Since there were 5 blocks that had the value of the mean on it, 5 out of 25, that was our most probable pick from the bag. But I want to get back to this, maybe we should take more than one block. And I think most people are pretty comfortable that if you want to make a guess about some population, that the larger the sample you have, the more confident that you can be in your guess about the population. Now, you may not have thought about it like that, but if I was trying to guess the average age of students in a particular college, do you think I would be better off randomly choosing one student from the population or randomly choosing 20 students from the population and trying to make a guess from 20 students? I think most people are comfortable thinking about, the more people that we have from a population of interest, the more confident we might be in our guess about what's going on. And this is true, if we want to bring this sort of more locally. I mean, if I've mentioned before, I think that I'm a golfer. I like to golf. And if you were trying to guess how good of a golfer I am, would you rather see one game that I play, or would you base your guess on seeing, let's say, 6 games? And I think most people are comfortable saying, if I saw you play 6 times, then I would have a better idea of how you played than if I just saw you play once. Okay? Likewise, as a student, it would be kind of weird if I gave you only one exam. That's a single sample, right? A sample of 1. I'm not sure I could be so confident in knowing how well you know the information. I think I'd be more confident if you had 3 exams or 4 exams or 5 exams. Because one exam, you might do exceptionally poorly on, and it doesn't really represent your population of knowledge, right? Or you might do particularly well on an exam, and you really don't know the information that well. And so if I based your grade on one exam, I wouldn't be as confident that that grade reflects your mastery of the knowledge than if I gave 3 or 4 exams, okay? So this is all related. In terms of the exams, I'm trying to make an inference about what you know, right? It's not just statistics, and when we talk about population, we're talking about, pharmaceutical research, or we're talking about political polling. I mean, the population I'm interested in here is sort of inferring about, the population of your knowledge of the material, right? When you're trying to guess about what kind of a golfer I am, the population there, I'm putting in quotes, is sort of like, all of my golf games or my potential ability. What is my average score? Okay? So that's really what we're getting at. If I'm, a physician and I want to know if there's, if your heart is healthy, I might take your pulse and listen to your heart with a stethoscope. But I'm not going to do that just once. I'm going to do that several times, and that's going to give me a better idea about what's going on, what's the underlying reality there. That's really what I'm talking about with the population. So, in this video, I want to talk about the mathematical bases of this notion that most people are comfortable with, and that is, taking a larger sample is probably going to make us more confident that with our inference, with our guess about some underlying population. So let's do this. This is going to take a while to unfold, and I think it's really important, and it's important enough to take some time to develop this concept. Because when you read this in the book, it can be potentially very confusing. I think it's the most difficult concept. And to be honest with you, I think a lot of people that teach statistics, some percentage, not sure they totally understand it themselves, okay? But that's just my judgment. Most people that teach the course do know it, but it's a difficult concept is what I'm trying to get across. So what I would like you to do is start a new page in your notebook, and maybe we can do the page landscape style, okay? Because I'm going to have a number of distributions here. Let's see, 1, 2, 3, 4, let's say 5 distributions, okay? And it would be nice if we could sort of see them all together. So I'm going to start with the distribution that we talked about in the last video. I need to make this a little bit smaller because I'm going to have a number of different distributions. And remember, this was, oh boy. Oh, well, we'll make that work, okay? And all the boxes are supposed to be the same size, but remember, we had our x values here, okay? And we know that this is the mean, and we know that there's some standard deviation. By the way, we could also, and we know that this is the mode, we could also get the range here without knowing the values of all the blocks, right? Because it's 1, 2, 3, 4, 5, 6, 7, 8, 9. We have a range of 9 here. And what I'm going to do is I'm going to disclose to you, I'm going to tell you what this distribution in this bag actually looks like, what the actual numbers are, because then we're going to develop this notion. I'm going to redo this graph too. Perhaps I should have done it before I started the camera, but that's okay. You can see me draw the graph again, okay? 25 blocks. 25 blocks. Not sure if that one was much better, okay? Got kind of skinny in the center. That's okay. So n equals 25 in this case. Again, it's small, it's manageable, it's something that we can look at and think about when we talk about real life populations, typically or often, at least theoretically, we're talking about n equals infinity or some large number, okay? But let's just develop the idea with the small population and understand that what we develop here is applicable to all populations. So I'm going to give you the scores here. The population in the bag has 1 10, 2 11s. I mean, we could put these in here. 3 12s, 4 13s, 5 14s, 4 15s, 16, 17, 18. Everybody with me? So the mean for this distribution is 14. And it has some standard deviation. We could calculate that. Certainly now you could calculate it, right? 1 10, 2 11s, 12s, 14, so on and so forth. So like I was saying, there are 5 blocks. There are 5 blocks with the number 14 on it, and 5 out of 25, so there's a 20% chance that we're going to pull one of those blocks. There's only a 4% chance that we're going to pull the block with 10 on it. There's an 8% chance to pull one of the 11s, 12% chance, 16, 16, okay. These are the percentages here which relate to the probability that we're going to pull a block with that number on it. Everybody with me? I mean, you need to understand that first. Since there are 3 12s, 3 out of 25 gives us a 12% probability of getting a 12, right? 16% probability of getting a 13, and so on and so forth. This is 18 out here. We have a 4% chance of pulling that 18, okay? Now, it's not surprising what happened during the last video, because the first number that we pulled out was a 14. I mean, that was unplanned. If you randomly, mix up the blocks, the highest probability is a 14. But I could have, that is, it's possible that I could have pulled the 18. That only happens 4% of the time. It only happens 12% of the time that I get a 16. Anyway. And then remember when we pulled that second block, it was a 15. Well, that's not surprising either, because that's the second, or tied for second, for the most probable outcome. Okay, so I pulled a 14 and I pulled a 15. What I'm going to do now is I'm going to create, let's do this, do that distribution. And I'm going to do 3 more down here. Okay, 5 distributions perhaps. And here's what I'm going to do. I'm now, instead of taking out a single block, I'm going to take out a sample of blocks. That is, a sample that's comprised of more than a single block. All right? And I'm going to change the sample sizes, and we'll see what happens. What I'm going to do here is, when I take out the sample, I'm going to calculate the mean for that sample, and then I'm going to plot the mean, that mean on a distribution. Okay, so let me do 2 silly ones first, and then I will do 2 realistic distributions. And these are going to be called sampling distributions of sample means. These are going to be called sampling distributions of sample means. Okay? So on our x-axis, like these were the scores, right? And I got the mean and standard deviation. For these sampling distributions of sample means, and you need to take this slowly and deliberately, okay? Instead of x values, what we're going to have on the x-axis are m values. And these are m's, as in Michael or Mary. These are not mu's, okay? So this is not the symbol for the mean for a population. These are m's, which are means for samples, okay? M represents means for samples. And I'm not putting any, I'm just putting these m's. There's no magic number here. I just want to show you that rather than x's on this axis, I have m's, okay? It's really a continuum, goes on indefinitely, okay? These are m's. Okay, let me do the first silly example, okay? And I can only do this example because of the size of the population that I have. It's very small. So what I'm going to do is my sample from this bag, my sample will be samples. This is samples because I'm going to take out repeated samples. I underline that for a reason. Okay, I want people to pay attention. I'm going to do multiple samples. Samples of sample size n equals 25. Samples of sample size n equal 25. Now, maybe some of you are scratching your head. It's like, well, that's kind of weird because there's 25 blocks in there. Yes, so let's do this. I'm going to shake these up randomly. I'm going to take out 25 blocks. I'm going to take out 25 blocks. That is all of them, okay? I'm going to calculate the mean for those 25 blocks. And what is the mean for the 25 blocks? What is the mean for the 25 blocks? It's 14. So I'm going to plot that sample mean here. 14. Now that does not represent one block. It does not represent one block of 14. It represents the average for all 25. Okay? It's a little bit of a silly example to begin with here. I'm going to put all the blocks back in the bag. Mix them all up. I'm going to take out another sample of 25. I'm going to calculate the average for those 25. What is the average? 14. I'm going to plot that. Stay with me, folks. I know what I'm doing. Put the blocks back in. Shake them all up. Take out a sample of 25. That's all the blocks. Calculate the sample mean, which is m, 14. I'm going to keep doing that, right? 14. I'm going to keep doing that. 14. I'm going to keep doing that 1,000 times, let's say. All right? And now what I want to do is I want to describe that distribution. I want to describe this distribution. And this is a sampling distribution of sample means with n equals 25 taken from this population. So I'm going to ask you, what is the mean for that distribution? Stay with me, okay? Don't make it harder than it is right now because it's going to get harder. Yeah, the mean for this is 14. Now, I'm going to have a new symbol here, and that is mu, the mean for this distribution, and it is a distribution of sample means. So it's mu with a subscript of m. This is the mean of all the sample means. That's how it has to be described, folks. Be deliberate. Take your time. This is the mean of all the sample means. This is the mean of all the sample means. And in this case, it's 14.00. Okay. And of course, when we describe a distribution, we want to also describe its variability. So this is M subscripted to a standard deviation. What is the standard deviation here? What is the standard deviation here? Yeah, there's no variability, right? So the standard deviation is 0.00. Every time we take out all 25 blocks and calculate the mean, we're going to get a standard deviation of those sample means of 0. Okay. I'm telling you that's a little bit of a silly example, but I hope you're with me in terms of what this distribution is. It's a distribution of sample means with an S. It's a distribution of sample means that are derived from each sample n equals 25. All right? Okay. I'm going to do the next example. It's another kind of a weird example, but I'm hoping that it will help to illustrate a point that I'm making. And that is, I'm going to do samples. I'm underlining that again because I'm going to take out 1,000 samples, okay? This is not the number of samples that we're taking. It's the size of the sample. And I know that other people who teach this course sometimes get frustrated because there's a difference between the number of samples that we take and the size of the sample that we take, all right? I can have a small watermelon and have 1,000 of them, or I can have a large watermelon and have 1,000 of them. The size of the sample is different than the number of samples that we do. The number of samples are 1,000, 10,000, 100,000, okay? This refers to the size of the sample. Samples of n equal 1, okay? Samples of n equal 1. So what I'm going to do is I'm going to take out one block and get the average for that block. Yes, you can have the average for one, okay? Again, this is a little bit silly, but it's going to help illustrate the point. And we already have 2 samples, right? We took out a sample yet for the last video. We had a block that had the number 14 on it, and I'm going to say what's the average for that block with 14? Well, it's 14. It's just an average of 1, right? We also took out a block that had 15, and I'm going to do another sample of 1, and this 14 again, okay? 14 again. I'm doing this all spontaneously here, folks. You're going to have to trust me. I mean, you can hear it, you can see it, right? Let me take out another block. There's a block with 11, okay? So that's down here, right? The average for that block of 11 is 11. Now, I'm going to keep doing this 1,000 times, 10,000 times. In computer science, this is called, in mathematics, this is called Monte Carlo testing. We start with something we know, we do a whole bunch of samples and see what happens. If we use samples of n equals 1, is it possible to get a sample with a mean of 10? Well, yeah, because here's the 10 right here, right? So we're going to get that. And we actually know how often we will get that if we do random sampling. That'll happen 4% of the time. Will we get a 17? Sure, it'll happen 8% of the time. Will we get an 18? Sure, it'll happen 4% of the time. Okay? and 16, and so on and so forth. We're going to keep taking samples. We're going to keep taking samples. And if we take 1,000 samples or 10,000 samples, what do you think that this is going to look like? Well, it's going to look like this. Of course, if we took out 10,000 samples, there's going to be more blocks, but it's going to have the same percentages here, right? If we do this 100 times, 20% of the time we're going to get 14s. 16% of the time we're going to get 13s, and so on and so forth, okay? It will really mimic the shape and the proportions here. What do you think the mean of all these sample means will be for this distribution? If your guess was 14.00, you are correct. That would be the mean of all the sample means. It would be 14. That's the mean of all the sample means. The standard deviation of all the sample means is going to be equal to the original standard deviation here. Okay? Now these two are sort of my bookends, and they're actually really silly because if we say a sample of n equals 1, in some ways that sort of defies the definition of what a sample is. A sample is more than 1, but we can do this technically. You would just take whatever block you have and then divide it by 1 to get the mean, okay? In this case, and there's nothing special about n equals 25, but the fact that in this case, the sample is the same size as the population. So we're always going to get 14 here from this distribution. 14 is our mean, and it will always be 14. In fact, could we ever get an average of 18 if we took samples of 25? The answer is no. We couldn't get a sample of 10, that is, with an average of 10, because we're taking out all 25 scores. Okay? But let's do a little bit more realistic sample, and let me do it this way. Let's do samples. I'm underlining that. There's a reason I'm underlining that, because I want you to know that we're going to plot a whole bunch of samples, 1,000 or 10,000 or 50,000 or whatever it is. Okay, samples, and the size will be samples of n equal 4. Okay, so what does that mean? This is a sampling distribution of sample means where samples are n equal 4 in this case. Well, what that means is I'm going to go into my bag. I'm going to pick out 4 blocks, okay? Samples of 4. So let's see. 1, 2, 3, 4. First one, 17. Second one, 10. Third one, 12. Fourth one, 16. So let's get the average for that sample. 16 plus 12 plus 17 plus 10 divided by 4. The mean for that sample is 13.75. So we're going to plot that. Okay? Now I'm going to put these blocks back in. This is always with replacement, random selection with replacement. Whoa, wait a minute. Let's take a break here. We did pick out a block of 10. They had 10 on it. Wow. That was kind of a rare pick, right? We picked out a 17 as well. But the mean for our sample of 4 was 13.75. Kind of cool. That's pretty close to 14, right? Okay, well, interesting observation, right? So let's take out another sample of 4, and I have another sample of 4. You have your calculator ready? 13, okay. 17, I'm going to put this into my calculator. 13 plus 17 plus 18 plus 13. We're going to divide by 4. The mean for this sample is 15.25. 15.25 was the mean for that sample, and that was a sample that included a score of 18, wow, another rare one, and 17. But what happens? 15.25 is not that far away from 14. Okay, let's do another sample of 4. The reason I'm doing this, low tech, you guys, I want you to see how this is developing. It may be boring for you, but next video and the one after that, I'm going to be asking you to remember what we did here, okay? Remember what we found. We're taking out samples of certain sizes from this population. Another sample of 4. So here we go. First block, 14 plus 16 plus 10 plus 15 equals, divided by 4, 13.75. And did we say that had a 10 in there too? No. Yeah, another 10. Wow. Okay. But our overall average for the 4 is 13.75. Okay. Let's do another one. Okay. Here we go. 12 plus 15 plus 11 plus 14 equals, divided by 4. So now we have a mean of 13. See what I'm doing here? I'm getting the mean for each of the samples. I'm plotting those means. That's why it's called the sampling distribution of sample means. Let's do one more for sample size of 4. Let's do one more for sample size of 4. Okay, here we go. 15 plus 11 plus 16 plus 12 equals 54 divided by 4, 13 and a half, okay? I'm going to keep doing this over and over and over and over and over and over again. And I think you might, well, let me ask you this question before I go further. What would be, take your time to think about this. If you need to pause the video, pause it, because I really want you to think about this. This will help you with your understanding here. What would be the highest mean that we could get for a sample of 4? And it's not 18, because we have to take 4 blocks from this population. There's only one 18, so the 18 has to be combined with 3 other scores, okay? So the highest that we can get for the sample of 4 could not be 18. It's impossible. Impossible. So what would be the highest mean that we could get for this distribution of samples of 4? Pause the video if you need to. What would be the highest? Okay, so to get the highest mean from here for a sample of 4, we would have to get this block, right? And we would have to get this block and one of these blocks. We would have to get that to get the highest. Now, in order for that to happen, this is a rare event, 4%. Plus, we'd have to add 2 other events that are pretty improbable, plus another one that's fairly improbable. Folks, let's think about this in common probabilities. The probability of a rare event happening and another rare event happening ends up being multiplied, but it gets smaller because these are decimals. I would ask you, what is the probability that you would win the lottery on the same day that you got hit by lightning? Well, that's virtually, it's so close to zero, right? What's the probability that you get hit by lightning? Well, it's some probability, right? What's the probability that you'll win the lottery? Well, it's some probability. Both are really tiny. If we need two of them to happen at the same time, it gets astronomically small. What we're talking about here is 4% times 8% times 8% times 12%. Percentages in decimals, that is, proportions. It gets very, very tiny. So I'm going to do it I'm going to do this because it is extremely unlikely that we get an 18 plus 2 17s plus a 16. We did see an 18, but it was combined with other numbers that were more probable. What would be that mean? 18 plus 17 plus 17 plus 16 divided by 4. The highest mean that we could get for a sample of 4 would be 17, and that would happen very rarely. It would be impossible to have a score of a mean of 18 with 4 blocks, because the 18 would be combined with 3 other blocks. What about the lowest mean for a sample of 10? What about the lowest mean? Well, that would mean we would have to get this, we would have to get this, this, and one of these. And in fact, the mean there would be 11. But we've already done 5 sample means, 13.5, 13, 13.75, 13.75, 15.25, and we're going to continue doing those 10,000 times, let's say, okay? Many, many, many samples, each of n equals 4. All right, are you with me? I'm extending this example for a reason. It's very difficult to understand this, okay? Now, when I now take all the means of the mean of the sample means, guess what I'm going to get here? If you guessed 14, you're absolutely correct, okay? And it will be 14. If I did 10,000 of these, it will be 14. I could probably do 1,000, and I'm going to get 14.00, okay? And it will have some standard deviation. We don't know what that would be. We know here it would be 0. We know here this would look like this in terms of how spread out. Here, though, we're getting a little bit of an inclination that the numbers are coming inward, right? The highest sample of 4 we can get is 17, and that would be really a strange random pull. Over here, same thing. The lowest would be 11. Okay. Let's move on. I'm going to do 10,000 of these, okay? Let's move on. And we'll now do samples of n equal, what do we want to do? Let's do 8, okay? Samples of n equal 8. What does this mean? It means I'm going to take 8 blocks out of here at random. So I really want to make sure all these are the same size. I want to make sure that we have an equal chance of getting the 8 blocks, an equal chance that any of those blocks can be part of this sample, okay? Okay, so here we go, 8 blocks. So samples of n equal 8. Here's our first sample. You got your calculator ready? Here we go. 13 plus 15 plus 12 plus 15 plus 17 plus 18, wow, plus 14 plus 14 equals, divided by 8, 14.75, okay? 14.75. So we're going to plot that average, that mean of that sample of 8. So you guys know what we're going to do next, right? Are you with me? Are you with me? I'm going to ask you to remember this process. So here we go. Let's put those back in. We're going to get this all. So that's 5. 3 more. Okay, here we go. Calculators at the ready. 16 plus 13 plus 16 plus 13 plus 10 plus 14 plus 12 plus 14 equals, divided by 8 equals 13.5. 13.5. Plot that. We'll do one more of these because I'm assuming that you're with me now in terms of what we're doing. We're pulling out these samples, okay? So here's a sample of 8, 5, 6, 7, 8. Okay, here we go. 16 plus 14 plus 13 plus 12 plus 15 plus 14 plus 17 plus 15 divided by 8, 14.5. Okay. I'm not going to belabor it any further. I'm assuming that you're with me in terms of what we're doing. I'll go in and I'll take out another sample of 8. I'll go in and take out another sample of 8. I'll go in and take out another sample of 8. I'm going to do that 10,000 times. Why am I saying 10,000 times? I really want folks to understand that it's samples of n equal 8. Each of the samples is 8 blocks. And I'm going to do that lots and lots of times for my sampling distribution of sample means. Okay? By the way, for 8 blocks, what would be the highest mean possible? And before people say, I don't know, how would I know? Well, I'm asking you to think this through. Figure outable, okay? To get the highest mean, I would have to have the 8 highest scores. Here, 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 here. That's 5, and 3 of these. What would that be? If I happen to pick that out, wow, that would be very unusual. Both 17s, the 18, 16, 16, 16, and 3 of the 15s divided by 8. Well, I made a mistake. 18 plus 17 plus 17 plus 16 plus 16 plus 16 plus, 2 15s. The highest possible would be 16.25. But I should really do that as a dotted line because that would be very unusual, very improbable. Remember, small probabilities end up getting multiplied. They become smaller and smaller. Probability of you getting hit by lightning, winning the lottery, and finding $100 on the ground is really, really small. If all of those things have to happen simultaneously. What would be the lowest sample of 8? Well, you'd have to have a 10 plus 2 11s plus the 3 12s. That's 6 plus 13 plus 13. The lowest possible would be 11 11.75. Everybody with me? When I say the lowest possible, you would need the 8 lowest scores. When I say highest possible, you would need the 8 highest scores, all at the same time. But most of the time, folks, we're going to be, guess what? Pretty close to 14. And that is the power here. And in fact, when I take 10,000 samples of n equal 8, guess what my mean for all these sample means is going to be? That's right, 14.00. Hey, and I'm not kidding, you guys. This is not my opinion. If we want to, we can go back to the quincunx, okay? Every time I flip that over, the majority of those ball bearings are going to be right in the middle. That's completely related to this. It has nothing to do with my opinion. It has nothing to do, I mean, it just happens based on probabilities. And then, of course, this distribution will have some standard deviation as well. Okay? Now, here's the question. So, we took 45 minutes to develop this. I think it's worth it because this is the conclusion that we come to is extremely important, number one. Number two, it's complex unless you understand how this works, okay? And I could take out samples of 4 or 8 or 9 or 16 or a sample of 17 or whatever, okay? Do you see a pattern here? And there's 2 patterns that I would like you to see. When we look at the sampling distribution of sample means, what's one pattern that we see? Well, the mean of all the means, do not try to shorten that or you will be incorrect. The mean of this distribution of all the sample means will be 14 in this case. The mean for all the sample means, taken all together, will be 14, will be 14, will be 14. Okay? That is, the mean of a distribution of sample means will be equal to the mean of the population from which the samples were taken. Dr. Speck, can you repeat that? I absolutely can. And you should be looking at this formula because this is the cheat sheet. The mean of sampling distribution of sample means will always equal the mean of the population from which the samples came. The mean of each of these sampling distributions of means will be equal to the mean of the population of individual scores from which the samples were taken. Rewind, listen, rewind, listen. It's extremely important. By the way, I am not saying that every sample will be 14. I'm not saying that every sample will be 14. I'm saying that the mean of all the sample means will be 14. That is extremely important, and often people, when they get fast and when they get sloppy, they're going to tell me, oh, the mean of a sample will be equal to the mean of the population that it was taken from. No, that's not correct. I'm not saying the mean of an individual sample. I'm saying the mean of all the samples in the sampling distribution will be equal to the mean of the population of individual scores from which they were taken. Okay. Let's pay attention to the variability of these distributions. Do you see a pattern here? It's like, Dr. Speck, I don't see a pattern because you didn't put in values here. The only values we have is this one and this one. Okay? Does anybody see it? What is the relationship between the size of the sample, okay, and the variability of the sampling distribution? You can sort of see it developing here, right? If we just take out samples of 1, we could get a 10, we could get an 18. Most of the time, we're going to get this. When we take out a sample of 4, the highest mean that we could get is 17. The lowest possible that we get is 11, and that doesn't happen very often. If we take out samples of 8, the lowest possible mean is 11.75. The highest is 16.25. By the way, those are equidistant from 14, right? But most of them are going to be in here. By the time we get out here, if we take out samples of 25, well, we know the standard deviation would be 0. Do you see the pattern here? Yeah, it's an inverse relationship. As we increase the sample size, the variability of the sampling distribution goes down. As we increase the sample size, the variability of the sampling distribution goes down. We see it here, okay? That's an inverse relationship. And so I'm going to get rid of this for now because that's a silly example anyway, okay? The standard deviation of a sampling distribution is inversely related to the sample size. Please pay attention. It's the sample size. It's the size of the sample that we took out, not the number of samples. So that's why I kept saying each of these. We're going to do it 10,000 times. Doesn't matter what, we just want lots and lots. We'll see this be a normal curve, okay? But this is an indication of the size of the sample. It's not how many samples, okay? Please make sure you get that right. So the sampling distribution standard deviation gets smaller as n gets larger. And this is how you would do this in a mathematical function. And it is directly related or proportional to the original standard deviation, okay? If you start with a distribution that's more variable, these will tend to be more variable, but the relationship still holds that it's inversely related to the sample size, okay? And in fact, I'm going to add one more symbol here. And you'll have to talk to a mathematician to understand why this is true. I don't know why. But it's actually inversely related to the square root of the sample size. Okay? These two patterns make up what's called the Central Limit Theorem. And I'm going to stop the video there, and we'll pick up exactly right there when we come to the next video.